A wave. The image that follows shows waves, visible as circular ripples, moving from the center and spreading out through a body of water. A wave can be defined as a disturbance that transports energy from one place to another. The waves in the water are called mechanical waves. Mechanical waves travel through surrounding matter called the medium. In the image, the medium for the waves is the body of water. You can create a wave in a body of water by using your finger or a block to tap on the surface of the water. By repeating this action, you can generate a sequence of waves. On a windy day, you can see mechanical waves and flags, as shown in the next photo. The fabric of the flags is the medium for these waves. When a mechanical wave is formed, energy is transferred to the medium, and the particles that make up the medium push or pull on neighboring particles. This pushing and pulling causes the particles of the medium to vibrate up and down or back and forth, relative to their original or rest position. The energy moves away from the starting point and travels through the medium. When a wave travels through a medium, the particles in the medium do not move that far from their rest position. And eventually, the particles of the medium return to their rest position, or really close to it. For example, when generating a wave using a coiled spring toy, a particular section of the spring toy moves up and down or back and forth. Eventually, each section of the toy returns to where it started. However, the wave travels all the way from one end of the spring toy to the other end. Another way to say this is that waves transfer energy from one place to another without a net transfer of matter. The medium of a mechanical wave can be a solid, liquid, or a gas. In the Explore lesson, you observed waves transmitting through liquid water and waves transmitting through a solid spring toy. You also observed two different types of waves. In longitudinal waves, the particles of the medium vibrate back and forth parallel to the direction that the energy of the waves travel. In transverse waves, particles of the medium move perpendicular to the direction that the energy of the waves travel. Not all waves are mechanical waves. You will explore waves that do not require a medium in Subunit 3. Stop and check. What is a wave? What is a mechanical wave? What is a longitudinal wave? Based on the animations you observed earlier, draw a model of a longitudinal wave that shows how the particles of the medium move. What is a transverse wave? Based on the animations you observed earlier, draw a model of a transverse wave that shows how the particles of the medium move. Wave characteristics. Each wave has characteristics that can be observed and measured. In the animation from Part 1, you worked with different models for waves that showed how particles in the medium can move. The diagram that follows shows a mathematical model of a simple wave. A simple wave has a repeating pattern with a specific frequency, wavelength, and amplitude. In the mathematical model, the peaks or highest points of the waves are called crests. The lowest point of the wave are called troughs. Simple mathematical model, position of particles versus distance. Wavelength, crest, amplitude, rest position, trough. Amplitude, the maximum distance the particles of the medium move from the rest position, is a wave characteristic called the amplitude of the wave. The amplitude of the wave in the mathematical model is marked with red lines. Notice that the amplitude is the distance from the rest position to a crest or from the rest position to a trough. It is not the distance from a trough to a crest. Amplitude or amplitude. Wavelength. Imagine generating transverse waves with a coiled spring toy. You hold one end of the toy and start from a resting position. Move the toy up, down, and back up to rest to generate one wave cycle. The wavelength is the distance traveled by the energy through that cycle. Moving from a crest to a trough and back to a crest is a complete cycle for a wave. The wavelength of a wave can be defined as the distance between two identical adjacent crests or troughs for one complete wave cycle. In the mathematical model, the wavelength is shown as the distance between two adjacent crests, as well as the distance between two adjacent troughs. In the models of mechanical waves that follow, wave A has a wavelength that is greater than wave B. Wave A, position of particles versus distance. Wave B, position of particles versus distance. Frequency. The number of waves that pass a fixed point over a specified amount of time is the frequency of the wave. Imagine tying one end of a rope to a tree and making waves by moving your hand up and down as shown in the illustration that follows. The distance you move the rope up and down determines the amplitude of the wave you generate. How quickly you move the rope up and down determines the frequency of the wave. One way to measure wave frequency is by counting the number of crests that pass a fixed point over a specific time period. The higher the number is, the greater the frequency of the wave. In the models of mechanical waves that follow, imagine that both wave A and wave B were generated in the same amount of time. The frequency of wave B is greater than the frequency of wave A. In the same amount of time, more crests pass by a fixed point for wave B than for wave A. Wave A, position of particles versus time, and wave B, position of particles versus time. The frequency of a mechanical wave is determined by how fast the particles of the medium are vibrating up and down or back and forth. The unit for frequency is the hertz, Hz, and is defined as the number of complete wave cycles that occur in 1 second. Note that wave frequency is not the same as wave speed. If you follow one crest of a wave as it moves from one place to another in a given amount of time, you can calculate the wave speed. To do this, divide the distance the crest traveled by the time that it took to travel that distance. The speed of a wave depends on the characteristic properties of the medium. There is a mathematical relationship between the wave speed, frequency, and wavelength of a wave. Wave speed equals wavelength times frequency. The wave speed remains the same when the properties of the medium do not change. In this case, the frequency and wavelength are inversely proportional. If the wave speed does not change and the frequency is increased, the wavelength is decreased. Likewise, if the wave speed does not change and the frequency is decreased, the wavelength is increased. Stop and check. What is the amplitude of a wave? What is the wavelength of a wave? What is the frequency of a wave? For waves traveling at the same speed in the same medium, how are frequency and wavelength related? Waves transfer energy. Wave energy and amplitude. When comparing two mechanical waves that have the same frequency, the wave with the larger amplitude transfers more energy than the wave with the smaller amplitude in a specific amount of time. Imagine tapping on a body of water in a repeating pattern with a block. At first, you tap as lightly as possible, transferring a small amount of energy. Waves with a small amplitude move away from the disturbance. Now, imagine tapping the same body of water with the block, with the same frequency, but this time you push down with as much force as you can with each tap of the block. Waves with larger amplitude are generated because you transfer more energy to the medium with each tap than you do to make smaller waves. In the models of mechanical waves that follow, both waves have the same frequency. Notice that wave B has an amplitude that is greater than the wave A. This means that wave B transfers more energy than wave A in a specified amount of time. Wave A, position of particles versus time. Wave B, position of particles versus time. Wave energy and frequency. When comparing two mechanical waves with the same amplitude in a specified amount of time, the wave with a greater frequency transfers more energy. In the models of mechanical waves that follow, both waves have the same amplitude. Notice that wave B has a frequency that is greater than wave A. This means that wave B transfers more energy than wave A over a specified amount of time. Wave A, position of particles versus time. Wave B, position of particles versus time. Stop and check. How is amplitude related to the energy transferred by a mechanical wave? How is frequency related to the energy transferred by a mechanical wave? A simple wave model shows repeating patterns. Based on what you have learned in the subunit, what specified patterns associated with waves are repeated and measurable? Wave A and B are mechanical waves. Each wave has the same frequency. Which wave do you think will transfer more energy in 5 minutes? Explain the reason for your choice. Wave A, wave B. Wave A and B are mechanical waves. Each has the same amplitude. Imagine that both waves were generated in the same amount of time. Which wave do you think will transmit more energy in 5 minutes? Explain the reason for your choice. Wave A, wave B.